The next idea that we want to port over from the real numbers is that of the multiplicative identity. We call the number 1 the multiplicative identity because for any number a, when we multiply it by 1 on the left, we get a, and when we multiply it by 1 on the right, we also get a. We'd like to find a matrix that should behave sort of like the number 1. To be able to pinpoint such a matrix, it's helpful to think about some small examples. So let's start with the matrix A, whose columns are 1, 3, and 2, 4. We want to find a matrix I that satisfies I times A is equal to A. To do this, it's helpful to first identify what the dimensions of I must be. The matrix A is a 2 by 2 matrix. In order for the product IA to be defined, I must be an m by 2 matrix. That way, the product IA is an m by 2 matrix. But if IA is going to be equal to the 2 by 2 matrix A, then m had better be 2 as well. This allows us to think about the matrix I as a matrix with 2 columns, each being 2-dimensional vectors. So I is a 2 by 2 matrix with columns u1, u2, v1, v2. If we write out the product, I times A, then because this example is small, we can easily write down the resulting matrix. The entries of this matrix are u1 plus 3v1, 2u1 plus 4v1, u2 plus 3v2, and 2u2 plus 4v2. Equating this with the matrix A, we can see we get a set of 4 equations in the 4 unknowns u1, u2, v1, and v2. We can translate this into the following augmented matrix. We can put this into reduced row echelon form by first subtracting twice row 1 from row 2. Next, we can subtract twice row 3 from row 4. We can interchange rows 2 and 3. Then we can scale rows 3 and 4 by -1/2. Next, we can clear the 4th column by subtracting 3 times row 4 from row 2. And we can clear the 3rd column by subtracting 3 times row 3 from row 1. This gives us a unique solution. u1 is equal to 1, u2 is equal to 0, v1 is equal to 0, and v2 is equal to 1. This tells us there's a unique matrix I such that I times A is equal to A. For reasons that we'll better understand later on, the matrix A was particularly nice, in that there is a unique solution to the matrix equation IA is equal to A. This is not always the case for all matrices. However, it does give us some insight into the type of matrix that we're looking for. The columns of this matrix are E1 equals 1, 0, and E2 equals 0, 1. If we remember back to our discussion on linear combinations, these are the 2 unit vectors corresponding to the positive x direction and the positive y direction. These 2 vectors are special in the sense that we can project onto the columns of any m by 2 matrix simply by multiplying A by either E1 or by E2. Moreover, the matrix I itself also poses a very special property that for any 2-dimensional vector v, whose coordinates are v1 and v2, I multiplied by v is the vector v. These 2 pieces of information give us a lot of information about what we can create for a matrix which might serve as a multiplicative identity. So let's consider another example. So we have a matrix A whose columns are v1 and v2, and this matrix is an m by 2 matrix. We're also going to take a matrix B whose columns are w1, w2, down to wn, which is a 2 by n matrix. We're going to show that the matrix I acts like a right identity on A and acts like a left identity on B. So if you want a challenge, you could take a second, pause the video, and try to work this out yourself. If you've taken a minute to pause the video and work on this yourself, here's the solution. We're going to use the fact that A multiplied by the vectors E1 and E2 give the columns V1 and V2. Computing the product AI, we first expand I as the array with columns E1 and E2. Gives us the matrix with columns A times E1 and A times E2. We recognize that those two columns are V1 and V2, and that is in fact our matrix A. For the second identity, we'll use the fact that each two-dimensional vector is fixed by multiplication on the left by I. This time, we expand B as the array with columns W1, W2, down to Wn. The product of these two matrices is defined to be the matrix with columns IW1, IW2, down to IWN. Since B is a 2 by n matrix, each of the vectors Wi is a two-dimensional vector. That means I times any of these w's is just w. And this, in fact, is the matrix B. So this gives us a partial answer to our original question in the 2 by 2 case. The matrix I is the unique matrix such that for all 2 by 2 matrices A, I times A is equal to A, and A times I is equal to A. It's important to note here that this is the only matrix that satisfies both of these equations for every single 2 by 2 matrix A. In the next video, we'll actually see that if we restrict to a single matrix, sometimes there's more than one. Now, if we want to think about matrices which have larger dimensions, then we need an analog of these two special vectors E1 and E2. We make the following definition. Fix an integer m. For each number I between 1 and m, the m-dimensional vector EI is the vector with a 1 in row 1 and a 0 in every row. For example, the two-dimensional vector E2 is the one with a 0 in row 1 and a 1 in row 2. The three-dimensional vector E2 has a 0 in the first row, a 1 in the second row, and a 0 in the third row. So it's important to note that EI can mean different things in different dimensions. With this new definition in mind, we can write down the m by m identity matrix. The m by m identity matrix, which we call I sub m, is the square matrix whose columns are given by E1, E2, down to EM, where EI is an m-dimensional vector. This is a matrix whose only non-zero entries are ones along the diagonal. This matrix has the special property that for any L by M matrix A and any M by N matrix B, IM is a right identity for A and a left identity for B. In particular, if we talk about a square matrix C, whose dimensions are M by M, then the identity IM behaves just like the number 1 in the sense that IM times C is C, and C times IM is also C. We note that when the dimension is clear from the context, we often omit the subscript and simply call the identity matrix I. For example, the 3 by 3 identity matrix, I, has 1s down the diagonal and 0s everywhere else. If we take the matrix, whose entries are columns 1, 2, 3, 4, 5, 6, 7, 8, 9, and we multiply this matrix on the left by I, we can see the result is exactly the matrix that we started out with. Similarly, if we take the same matrix and we multiply it on the right by I, which is exactly the matrix that we started out with.